Welcome to our presentation on mastering panel data estimation, covering the theory and practice from fixed effects to random effects, often demonstrated using software like EViews. As the quote from Gujarati highlights, panel data is a powerful tool that allows us to explore more complex behaviors and enrich our empirical analysis beyond what's possible with simple cross-section or time series data. This session will guide you through understanding when and how to apply these advanced techniques effectively.
Following our last discussion on the types of data, this slide highlights the core problem with simpler regression methods: ignoring heterogeneity. Heterogeneity refers to the unobserved, unique differences that exist between individual units, whether they are firms, countries, or people. Factors like management quality, cultural norms, or specific geographical advantages are often unmeasurable, yet they profoundly impact our variables of interest. Traditional time series data, which tracks one unit over many time periods, n equals 1, t greater than 1, and cross-section data, which observes many units at a single point in time, n greater than 1, t equals 1, are limited in their ability to account for these unobserved differences. They either focus on one unit's evolution or many units' snapshots. Panel data, however, combines both dimensions, observing many units over many time periods, n greater than 1, t greater than 1. This rich structure is crucial because, as the slide states, pooled OLS treats all units as identical. It ignores these unobserved unique factors, which ultimately leads to a critical issue: omitted variable bias. This bias results in unreliable and misleading coefficient estimates. To properly address this fundamental challenge, we need a more sophisticated approach. Panel data models are designed precisely for this purpose. Let's explore how they do this in detail.
Choosing the right estimator for panel data is crucial and should never be a guess. We follow a clear decision framework, guided by statistical tests. The first question is fundamental. Do you have panel data? If not, standard OLS or other non-panel methods would apply, but for panel data, we move to the next step. The first diagnostic test is the redundant fixed effects F-test. This test checks for the presence of significant unobserved heterogeneity across your units. If the null hypothesis, that there is no heterogeneity and all individual effects are redundant, is accepted, then you can use pooled OLS. However, if the null is rejected, it means heterogeneity exists, and pooled OLS would be biased. In this case, you must proceed to choose between fixed and random effects. This is where the Hausman test comes in. It helps you decide between the fixed effects model, or FEM, and the random effects model, or REM. The null hypothesis for the Hausman test is that the individual effects are uncorrelated with your regressors, which is the key assumption for the random effects model. If the Hausman test's null hypothesis is accepted, implying the effects are uncorrelated, then the random effects model is the more efficient and consistent choice. But if the null hypothesis is rejected, meaning there's a correlation, then the fixed effects model is the appropriate choice to ensure consistent and unbiased estimates. This framework prevents you from guessing and ensures you select the mathematically sound model for your specific data, thereby avoiding bias and ensuring the reliability of your findings. Let's delve into the core ideas behind fixed and random effects. This matrix summarizes the key trade-offs between pooled OLS, fixed effects, and random effects in panel data analysis. Pooled OLS is the simplest, assuming no individual effects, but is highly biased if heterogeneity exists. Fixed effects treats individual effects as constant parameters, providing consistent estimates even if these effects are correlated with your independent variables. However, it consumes degrees of freedom and cannot estimate coefficients for time-invariant variables. Random effects assumes individual effects are random noise, leading to more efficient estimates and allowing for time-invariant variables. Crucially, random effects requires the strict assumption that individual effects are uncorrelated with your independent variables. If this assumption is violated, the estimates will be inconsistent. In summary, fixed effects is often considered the safe choice for its consistency, while random effects offers efficiency but demands stricter assumptions. This slide presents the fundamental equation for panel data, which is crucial for understanding how fixed effects and random effects models work. The equation is YIT equals beta XIT plus alpha IT plus UIT. Let's break down each component. YIT represents our dependent variable, or outcome, for cross-section unit I at time period t. For example, if we're studying countries, I would be a specific country, and t would be a specific year. XIT represents our independent variables, or predictors, also varying across units and time. Beta is the coefficient we aim to estimate, showing the effect of XIT on YIT. The term alpha IT is the individual effect, capturing unobserved heterogeneity specific to each unit I. This could be anything unique to a country, like its culture or institutional quality, that remains constant over time. Finally, UIT is the idiosyncratic error, representing all other unobserved factors that vary across both units and time. The core theoretical question in panel estimation, highlighted on the right, revolves around how we treat this alpha IT term. Is it a fixed, unobserved constant that we need to estimate for each unit, or is it a random variable, essentially part of the error term? The fixed effects approach estimates a distinct intercept, alpha IT, for each cross-section unit, treating it as a fixed constant. This controls for all time-invariant unobserved characteristics. In contrast, the random effects approach treats alpha IT as a random variable with a specific variance, sigma alpha squared, assuming it's uncorrelated with the other predictors. Understanding this distinction is key to choosing the correct model for your data.
This slide outlines critical assumptions for valid economic analysis and discusses robustness. First, strict exogeneity requires that the error term is uncorrelated with past, present, or future regressors. Second, cross-sectional independence means that errors between different units, e.g. Unit A and Unit B, must not be correlated. Third, homoskedasticity assumes that the variance of errors should be constant across all observations. This assumption is often violated in practice. For example, large firms often have larger variance in their financial data than small firms. To ensure the robustness of our results, especially in panel data, which is prone to issues like heteroskedasticity, it's crucial to always consider using robust standard errors. In software like EViews, you can choose methods such as white cross-section or cluster robust standard errors. This adjustment does not change your coefficient estimates, but corrects the standard errors, ensuring that your t-statistics and, consequently, your p-values are valid for hypothesis testing.
The very first and most crucial step in any panel data analysis is to properly structure your data. You cannot run a panel regression on a standard, unstructured workfile. As shown on the left, you need to open the workfile structure dialog in your statistical software, in this case, EViews. From the drop-down menu, select Dated Panel as the workfile structure type. Then, you must specify your panel identifier series by indicating which variable represents your cross-section ID, here ISO code, and which variable represents your date or time ID, here year. EViews, or any other statistical software, needs these identifiers to understand how your data is stacked, meaning how individual units are observed across different time periods. Without this proper setup, the software cannot correctly perform panel data estimations. The image at the bottom clearly illustrates this transformation. From a simple list of observations, your data is converted into a structured panel where each country's observations are organized by year, ready for analysis. This slide demonstrates how to access and configure the equation estimation interface in EViews. First, navigate by going to Quick, and then selecting Estimate Equation. Once the Equation Estimation dialog box opens, you'll see several tabs. The Panel Options tab is crucial when working with panel data. This is where you select the estimation method, choosing between fixed, random, or none for the individual effects. The highlighted section shows method, with fixed currently selected, and random and none as other options. Additionally, the Options tab allows you to specify the covariance method. For robustness, it's a best practice to select a method like white cross-section or other robust standard errors to correct for potential heteroskedasticity in your panel data. This ensures your statistical inferences are valid. This slide introduces our case study using the Penn World Table 6.1 extract. Our objective is to examine the solo growth theory within a panel data framework. The dependent variable for our analysis is GDP per capita relative to the USA, denoted as Y. For our independent variable, we will be using the population growth rate, specified as the first difference of the log of population, d log pop. The dataset covers 208 countries over the period from 1950 to 2000, forming an unbalanced panel. When working with panel data, it's crucial to inspect whether your panel is balanced, meaning all countries have data for all years, or unbalanced, with missing observations. While software like EViews handles unbalanced panels automatically, we must always be aware of potential missing data, which can affect our estimates. We begin by estimating a fixed effects model. EViews does this using the within transformation, also known as the least squares dummy variable, or LSDV approach. This method effectively removes the time-invariant individual effects, effectively inserting a dummy variable for each country to control for all stable, unobserved characteristics. Looking at the regression results, we see the coefficient for population growth, d log pop, is negative 901.0468. This result is highly statistically significant, with a p-value of 0.0000, indicating a strong negative impact. The R-squared values, while seemingly low, are higher due to the inclusion of these cross-section dummy variables, which account for a significant portion of the variance. Now we move to step 4, testing for fixed effects. This is where we run the redundant fixed effects test, often referred to as the F-test, to decide whether our panel data model needs to account for individual fixed effects, or if a simpler pooled OLS model is sufficient. The null hypothesis of this test is that there are no fixed effects, meaning that all individual specific effects are the same and thus redundant. We look at the prob values for both the cross-section S statistic and the cross-section chi-square. In this case, both are 0.0000. As highlighted in the decision section, a probability value less than 0.05 leads us to reject the null hypothesis. Our p-values are indeed 0.0000, which is significantly less than 0.05. Therefore, we conclude that fixed effects are necessary and pooled OLS would be biased. The validation section on the right reinforces this by stating that we should never assume fixed effects are better. We must test it. If the p-value were high, greater than 0.05, it would imply that individual effects are redundant, and we could simplify to pooled OLS. But since our p-value is low, the individual effects are significant and must be included in our model. Now we move to step 5, estimating random effects, GLS. The random effects, or RE, model assumes that the differences across countries are just random noise. This is a stronger assumption than fixed effects, but it offers a benefit. It saves degrees of freedom, which can be important with smaller datasets. As you can see in the EViews output, the method is indeed Panel EGLS, Cross-Section Random Effects, Swami and Aurora Estimator of Component Variances. When interpreting the results from a random effects model, it's crucial to focus on the weighted statistics, as indicated by the blue arrow on the slide, since the RE model employs a generalized least squares approach that weights observations to account for the composite error structure. The Houseman test is our final step to choose between fixed and random effects. The null hypothesis of the Houseman test states that the random effects model is consistent and efficient, implying no correlation between the unobserved individual effects and the regressors. From the test results, we see a p-value of 0.0000, which is significantly less than our standard significance level of 0.05. Therefore, we unequivocally reject the null hypothesis. This means the critical assumption of the random effects model, that individual effects are uncorrelated with the regressors, is violated. The verdict is clear. When the random assumption fails due to a low p-value, we must use the fixed effects model to avoid biased estimates. This holds true even if the random effects model might, in other circumstances, offer smaller standard errors. The fixed effects interpretation relies on within variation. This means we are asking, if this specific country increases its population growth, what happens to its GDP? Looking at the results, the coefficient for D log pop is negative 901.0468. This means that in the fixed effects model, a 1% increase in population growth is associated with a 901 unit decrease in relative GDP, holding country-specific characteristics constant.
This slide outlines the best practices for conducting panel data estimation. First, it's crucial to properly structure your data by defining the cross-section and date IDs. Second, always inspect your data to understand if it's balanced or unbalanced. Third, when you begin estimation, start with a fixed effects model. Fourth, rigorously test the necessity of fixed effects by running a redundant fixed effects test. Fifth, compare fixed effects with random effects by performing the Houseman test to determine the most appropriate model. Finally, refine your model by checking for heteroskedasticity and considering white cross-section robust standard errors. The overarching principle is that good econometrics emphasizes diagnostics over blindly running regressions. Allow statistical tests such as the F-test and Houseman test to guide your model selection and ensure robust results.
This slide provides a quick reference for common EViews commands used in panel data estimation. While the graphical user interface is excellent for learning, mastering these command line syntaxes can significantly accelerate your research workflow. Here you'll find commands for fixed effects estimation using equation eq1.ls cx equals f, y, c, x1, x2, and random effects estimation with equation eq1.ls cx equals r, y, c, x1, x2. We also have the command for the redundant fixed effects test, which is eq1.rfx, and the Houseman test from an RE equation, freeze tab 1 eq1.ranhouse. Finally, to address common issues like heteroskedasticity and ensure robust inference, you can implement robust standard errors, such as white cross-section, using equation eq1.ls cx equals f, cove equals cx white, y, c, x1, x2. These commands are essential tools for efficient panel data analysis in EViews. This brings us to the end of our presentation. Here are some references and further reading that were instrumental in preparing this material. Gujarati, D. N. 2020, Basic Econometrics. Baltagi, B. H. 2005, Econometric Analysis of Panel Data. EViews User Guide 2, Panel and Pooled Data. And EViews Illustrated, Chapter 11. For your next step,